Hi. So, welcome to this lecture where we basically go through the summary of all that we have learned about second order linear homogeneous ordinary differential equations. So, this is a very general type of second order linear homogeneous ordinary differential equation where x is a function of time, and this is a second order because x has been differentiated twice. X double prime plus b is a constant, which is a coefficient of x prime, first differentiation of x with respect to t, plus another constant c, x is equal to 0. It's homogeneous because the right hand side, or the input to the system, or the external force on the system, is 0. Okay, so this again is modeled on this example where there's a mass which is suspended from the ceiling by a spring. There are various forces acting on it, as we have already discussed many times before. This is the acceleration multiplied by the mass, which gives the force downwards. There is the spring constant, and multiplying that is the displacement of this of the body, which gives the force upwards if the body is moving downwards, the opposite pull. This, of course, is the frictional constant multiplied by the velocity, which gives the resistance, air resistance or friction, while this body is moving or oscillating up and down. So this is just an example. Various other examples, occur in nature, which give rise to this exact same kind of differential equation, second order linear homogeneous with constant coefficients. Now we have learned how to solve this differential equation. We tried this solution, so we called it the trial solution. We tried an exponential solution for xt. We tried it with e to the power mt, where m is a constant. The objective was to find that m so that this actually becomes a solution of this differential equation. Once you put that in, we got what is known as the auxiliary equation, where everywhere there is a differentiation term, you get an m. Here there's a double differentiation, so you get m square. Here there is a differentiation of only one time, so you get m. There's no differentiation, you get 1, like that. So that's the auxiliary equation. It's a quadratic equation in this unknown constant m. The task was then to find the roots. Of course, given these are the two constants in this, or the coefficients of this polynomial in m, then the two roots were m1 and m2, and they were given by the standard formula for a quadratic equation. Plus with m1 minus the root term with m2. That's just how I've named them. So just going over what we have learned so far, the general solutions for this type of second order linear homogeneous equation, differential equation with constant coefficients. So as you can guess that depending on how the terms b and c can be, you can get various cases, you can get various differential equations. So from here, one of the cases you can, now going over them, the first case that we have learned was the case of underdamping, where this b squared term is less than 4c. In other words, this is an imaginary term. So in that case, both m1 and m2 were complex numbers, but you can actually write them down as m1 equals, a real part plus an I into some real number, positive real number. So this is the imaginary part, and of course this is the complex conjugate. M2 is the complex conjugate of m1. So the underdamping happens when this discriminant is like that, when it is b square is less than 4c. In that case, we found that the general solution was given by this term. This is the decay term, decay in the amplitude, and this is the sine, or the wave term, the cosine and sine, which actually makes the body move up and down with a frequency omega. Okay, these are the constants. Of course, we've used some notations here just to simplify the writing. So instead of b by 2 here, we've used r instead of this whole square root term, which is now an imaginary term because we have b squared less than 4c. We called it I omega. So with these kind of notations, this is the simplified form of the general solution. This term is the decaying term. It's the amplitude, depends on time with a negative sign here. So as time increases, the amplitude of this wave actually decreases. So it starts out with an oscillation, and then it goes on for a while before this term decays to 0. As t goes to infinity, this term goes to 0. So the amplitude of the oscillation becomes absolutely 0. So it comes to a standstill. That's why the term underdamping, because it is not damped so much. The resistance is not very heavy. It goes on for a while. The oscillations will continue before it comes to a standstill. One of the extreme cases of this is a subcase where this term b square, obviously it's not just less than 4c, it is actually 0. What happens if it is 0? Then obviously this term, the amplitude term is just 1. So there is no decay in that. The amplitude is a constant 1. In that case, the body then goes on, carrying out the oscillation without any damping or without any decay in the amplitude. So it goes on and with the same up and down movement forever. So that's the undamped. B0 means that there is no resistance term. This B signifies the air resistance or the friction in the system. Then we come to the case of overdamping, where b square is greater than 4c, in which case we know that now this is a real term. It's no more an imaginary term. So m1 and m2 become real numbers. Okay, obviously this has always been real. Now with b square being more than 4c, this part will be real too. So in the case of overdamping, the general solution was just simply the first form of general solution that we have learned, some constant times e to the power the first root t plus another constant n into e to the power the second root t. If you want to, you can write it in this form also, e to the power minus rt, where you have written b by 2 as r again. And since now this is no more an imaginary term, we don't need that I here. It's just a real term. It's a positive number. So you can use m1 and m2, or replace m1 and m2 by these notations, and you can take out e to the power minus rt term here. You're left with another function. This again is a decaying function. Okay, the overdamping comes because this function does not really go up and down. It sort of decays all the while. This adds to the decay as well. Okay, this function is an increasing function and this function is a decreasing function. But overall, this function, because this function is less than this function, the effect of this function is sort of always less than equal to this function here, and then this decay part adds to it to make the whole general solution decay. And we have discussed the graph of this in the video where we have figured out the general solution for overdamping. The whole solution decays in a constant in a smooth manner, and so the overdamping is called overdamping because if you give it a pull and you let it go, it does not oscillate much. The amplitude kind of decays from there on, and then it comes to a standstill very fast. Okay, so therefore there is overdamping or over resistance. Now, this was the critical case and it's named critical damping, or the case of resonance, where b squared was equal to 4c. In other words, this term was 0. In the case that these two terms are 0, then obviously both m1 and m2 are minus b by 2. So they're equal and they're real. In that case, we found out by a use of L'Hopital's rule and limits and a lot of arguments which we have said in the video where we worked this out. Then we found that the general solution for this was given by this decay term and then this increasing linear polynomial, which is a polynomial of degree 1. And this is the solution which plays out very interestingly sometimes, as this part is an increasing part. In other words, it's a function which is increasing with time. As time goes to infinity, this function goes to infinity. But this is the decreasing part, this decreasing function. As time goes to infinity, this function decays to 0. So how this product plays out is very interesting. So if r, as we said in the video elaborately, if r is a very small number, and so the decay will be very slow, in that case, up to a certain point, this is the dominating factor for the solution, and so the function can grow as time grows. In other words, the displacement of the body can be more than the initial displacement that is given to it. And then after a certain while, when this the effect of this decay does kick in, then this becomes the more dominating function in the product, and then the general solution keeps on decaying from there on, and so this body will then come to a standstill, will come to a halt. But before that, if the value of r is very less, then the oscillation can become actually more than the initial displacement that is given to it. Very interesting case where it sort of, takes up, some kind of an energy on its own, and it keeps moving more than what was expected of it. And then finally, when this factor kicks in, it can sort of come to sense and go to a standstill. As I said, the most famous example of this was the Tacoma Bridge collapse in US, Washington, in the 1940s, where the bridge went through the same kind of resonance and it collapsed. And that's why this case is very, very interesting, and it needed special attention. So that's about the second order linear homogeneous ordinary differential equations with constant coefficients, the various cases. And I think we will finish it here. We will continue with, in the next few lectures, we will then move on to differential equations where instead of them being homogeneous, you will have some function term on the right hand side. So that makes the system more dynamic, and we will tackle those differential equations in the next few videos. Thank you very much.